Hello, everybody. Welcome back to Calculus. So we have reached chapter 6, and this is a chapter on applications of integrals, right? So we will study a sort of a variety of applications that involve integration. And before we get into the main part of section 1, I am going to have a sort of a comprehensive lecture on what definite integrals are. And so I hope you will pay attention to that because that really will help you understand what integrals are all about, okay? And then we'll go into the specific topics of section 1. So here we go, section 6.1. So what exactly is an integral? What is this thing that we have been calling a definite integral? The definite integral of function f between a and b. And so this is the picture, right? And we have, now, by the way, if you say the answer is, well, you take the derivative, antiderivative, capital F, and you evaluate the antiderivative, any antiderivative of lowercase f at b and a, and then do subtraction. That is sort of correct, okay, because that's what the fundamental theorem of calculus tells you. However, my question was, what is this integral? Not how you find it, okay, or how you evaluate that. If you are asked to find the value of this, or how you find the value of this, this would be an appropriate answer. But you did not answer the question of what that is, okay? It's almost like saying, if I ask you, what is lasagna? And then you proceed to tell me how you cook it. And then I said, no, I didn't ask you how to cook it. I said, what is that? Okay, so there's a very important difference between these things. All right, so this is how to evaluate that. Okay, but not how you, or what this is. Okay, so you have learned so far that this is the area under F over this interval from A to B. And that's okay, assuming that F is greater than or equal to 0. But if you imagine, or if you think about what we actually did, we we divided A into a bunch of subintervals, AB into a bunch of subintervals. And then for each subinterval, we picked a point which is supposed to represent that subinterval. And we evaluate the value of function f at that point. And we made that as a representative height for that rectangle. And then we added the rectangular region areas. All right, so basically what we have here is that for each x on, I should say on an interval, for each x on this interval, there is a value, f of x exists or is assigned, right? I mean, that's what a function is. A function, f is an assignment of from any point x, or from each point x to a real value. That's a real valued function. So for each x on AB, there is a value which is assigned to that x. And so every point has a value which could be different from point to point, even if the points are infinitesimally close to each other. And then we actually, in a sense, add those values. Now, of course, it's impossible to add infinitely many values. So let me see if I wrote this right. Then we add those values assigned at each x. And that is sort of true, except we can't add infinitely many things. And that's why we added finitely many things, a huge number of rectangular regions. And then we took the limit, okay, as n went to infinity. So it is sort of like a generalization of addition. And that is probably the best way to understand this whole concept. All right. Now, let's say you have the number of customers. Okay, so you have some store, you work at a store, And you're open 5 days a week. So you have this many people on Monday. And then you had more people on Tuesday, and you had a lot more people on Wednesday, and maybe not many people on Thursday. And maybe you had a decent crowd that came to visit your store on Friday. So this will be Monday, Tuesday, Wednesday, Thursday, and Friday, right? And if I ask you how many people came to visit your store this week, Monday through Friday, what you do is, okay, well, it's easy. You just add these 5 numbers, okay? And that, in a sense, is the finite version or a discrete version of integration. So you just add these things up, okay? So this, you can call this an accumulation of all those numbers that are shown on this graph, right? And this is a finite case. Again, this is a discrete case, right? And then the opposite of discrete. Okay, so this is a discrete. Opposite of discrete is this word continuous, which we learned in chapter 4. I believe it was section 2.4. So the accumulation, the discrete case is simply the addition, but accumulation in a continuous fashion or in a continuous version is called integration. All right, so think of an integration or integration technique or integration period as a sort of accumulation generalized in a continuous way. So basically, instead of that, you just have this, some kind of a function, and you just keep adding and adding and adding these things, and that becomes your integration, right? Let's say instead of 5 bars, you are, this is for 1 week, right? Let's say you have 52 weeks, that would be the entire year. And then you collected the number of customers over, let's say, 20 years. Now you have 20 times 365 days. You have a bunch of these days. So you have a bunch of these, bars going up. But you still have a finite number of bars, and you add them together and you have accumulation. And it's a discrete addition. Now, if you keep generalizing this, and if you have a value assigned at each point, then you have integration. So here's another example of this. And this is something we will study more deeply or more specifically in chapter 6. And I have sort of mentioned this before. If you have a rod or a stick, and for each X, by the way, this rod is made of different material and different parts. Maybe over here it's light and this is heavy here. Maybe it's much lighter here. Different alloys or different kind of metals are used to create this rod. For each X, density is defined. And the density, delta X, is defined. Sometimes it's called delta, sometimes it's called rho of X is defined, all right? And then the mass, again, the idea that if you are to follow the idea of Riemann sums, what you can do is you cut this rod into small pieces, and then you say, well, each of them is pretty much uniformly made, because these are small enough. And so each piece is going to weigh a certain weight, or you have certain mass. You add up all those things, all these pieces, and you have the total mass. That's exactly what we did in defining the definite integral as a limit of Riemann sums. Okay, so for each X, density is defined. The mass is going to be the integral from this point to this point, from A to B, of the density function. All right. Now, you could think of this as an accumulation or addition of these small pieces, right? Or you can just go ahead and represent the density as a function like that, right? So there is no difference between what we did here and what we do here, okay? And so that idea of accumulation or general or continuous addition is what the idea of definite integral is. Here is perhaps a more timely illustration or analogy. Okay, so let's say this is the number of new cases of COVID-19, and you have the day 1, January 1st, to day 365, okay, on a particular year, let's say 2020 or 2021 maybe, right? And then you, so this is f of x could be the number of new cases of COVID-19, right? And of course, x is 1, 2, 3, and x is defined as any positive integer from 1 to 365. So you have 365 bars, okay? Some parts are bigger, some days it's a lot less, and so on, right? So, I mean, this, if you look at this, you have 365 bars. And so it sort of looks like a, continuous function. It's not continuous because you just have bars and not, a smooth line or curve or something like that. But if you just basically, add up all of these numbers from 1 to 365. Now, again, this is not correct, right? Because you just have a bunch of bars. But that is similar to fx is an approximation for, the heights of these bars. And so this is very much like the sum of each day, right? Xi here, right? And by the way, this is the total number of new cases for the entire year. Okay, so again, think of integration as addition, taken to the extreme, or taken in an infinite or continuous ways. And also another helpful thing is, okay, instead of having bars, let's say here you had 200 new cases. So instead of having this, height 200 bar, think of having a bunch of Lego pieces. Okay, so here you have 200 Lego pieces. Okay, and the next day, let's say you had 300 people. So you have 300 Lego pieces. And then you have, so each Lego piece represents a new case for each day, right? And then this really just has to do with what? The total number of Lego pieces. I guess I should say that this is a trademark, all right? So the rights are protected. Okay, all right. So the registered trademark, okay. A total number of Lego pieces is basically the accumulation, the addition of all of these Lego pieces that you see for each of these bars, okay. And so think of that, and the total number of Lego pieces is like our answer for the integral. Right. What's amazing is that if f is continuous, we can still define this sum as the limit of Riemann sums, which is, of course, our definite integral. And the fact that if f is continuous with an antiderivative, we can actually evaluate this total accumulation by evaluating the antiderivative at 2 endpoints. That's a surprising part, okay? But the idea of what the definite integral is really has to do with this accumulation, all right? Maybe one last illustration so you can remember, all right? And maybe this will encourage you to exercise more. Let's say you have a 30-minute workout, okay? And you have, if you get on the treadmill, and some of the modern treadmills have all these fancy graphs of your workout, and it'll tell you, okay, so this is, you start off easy, and then what is this? Maybe it's a number of calories that you are burning, you're using, at every minute of this. And maybe you start off slow because you're warming up, and then pretty soon you're working really hard and you go to a steady level of calorie. And if you, depending on what kind of workout you choose, some of them are like rolling hills or cardio exercise, whatever. And so this may be the calories you are burning per minute. All right. So in the first a minute, you have burned this many calories, and then this and this and this, and you basically have 30 bars, but they're continuous or almost continuous. Okay. If you take the integral, which is the area under this curve f, right? Again, this is going to be the total calories burned for the first 30 minutes. And how did you figure this out? Well, you add the calories burned in the first minute, second minute, third minute, and so on. And so again, this is practically a sum, okay? And think of this as an accumulation. That is really the key word to understanding what definite integrals are, okay? So with that in mind, okay, if you understand this concept, all right, it's not just whatever this is, how to calculate this. I don't even know what I'm calculating, but this is how I calculate it. And if I spit my answer, I get the right, I get my points, and I graduate. That's cheap, all right? If you really want to understand calculus, this is what you need to know about integration, all right? And surprise, surprise, the fundamental theorem actually told you that this process of adding turns out to be the opposite or the inverse of differentiation, which was to find the rate of change, okay? So with that understanding, you will be a lot better students in calculus as you move into section 1 of chapter 6, how you apply integrals. All right, so now let's look at the specifics of section 6.1.